Welcome to WPI's Dynamics Laboratory. I'm Professor Norton, and I'm going to give you a demonstration of this CAM Dynamics testing machine, which you see before you. Let me explain what it is and what it does, and then we'll run it for you in a minute. There are two cams on a very large camshaft right here, and those two cams are driven by a motor which is down below that you cannot see. The motor drives through a belt into this flywheel at one end of the shaft. The power comes in the shaft at this end. There's a torque transducer, which you can see in blue right there, which allows us to measure the torque instantaneously on the shaft. There is then a commercial bellows-type coupling, which connects that piece of shaft to the next piece. It goes through a shaft encoder at that point, which gives us a train of pulses of something of the order of 4,096 pulses per revolution coming out of that shaft encoder. Another set of bearings. There actually are three stub shafts here, one there, one here, and one at the other end. So this stub shaft couples into another commercial coupling, and this is removable. We can replace this with different coupling designs. This has a helical type coupling in it at present, and that has a relatively soft torsional compliance. We can put stiffer or softer couplings in that to demonstrate the effects of torsional stiffness in the shaft. That then couples into the main camshaft, which I pointed out to you earlier, on which sit these two split cams. Now let me see if I can show you the splits by moving them just a little bit. I don't know if you can see it from that angle, but there is a split in the cam right there. The cams are made in two pieces. You can see the split there as well. And that's so they can be clamped around the shaft without having to disassemble the entire shaft. This is very common in industrial machinery to split the cams, because if you have a machine that is, for example, 20 feet long with a camshaft of that length, you don't want to be pulling that 20-foot long camshaft out every time you need to change out a cam. So in that case, you would split the cam and take it off. That split, as you will see when we take some measurements, is going to show up in our dynamic measurements. The cams drive, in this particular arrangement, what's called an oscillating follower train. It's a set of links and levers. A little hard to see from this angle, but we'll show you a close-up of it a little bit later. But the main lever that is riding against the cam is down here. There is a fixed pivot, a pin, to ground at this point, just below my pen. And I think you perhaps can see from the angle you're now looking one roll of follower running against the cam under there on this arm on the right. In the back, not visible to you at present, but which we'll show you later, there is a connecting rod that runs from that lever at the bottom up to the top. Here's the top of the connecting rod here, and that in turn couples into another rocker. So we have in effect a 4-bar linkage here, with link 2 being the big link down below. Link 3 I would call the coupler or connecting rod, and I would call this link 4. This is my output link, and in a real machine, which we'll show you in a different film, this would do some useful work, perhaps add a part to a product on an assembly line or some such. This is doing nothing. This is just a demonstrator machine, so we end the linkage here, but normally that would have some other stuff connected to it and go do something to a product. We have this instrumented. In addition to the torque transducer that I already pointed out to you, we also have accelerometers here and here on the end effector portion of the link, which is to say the output end of link 4. Link 4 is pivoted right here. There are a bunch of holes in the link, which you can see. That allows me to move that accelerometer to different locations on the link and see different effects of its modal vibration. Not visible from your present vantage point, but we'll show you a close-up of them in a minute, is a linear variable differential transformer. That's quite a mouthful. It's shortened to LVDT usually. That transformer lets us measure the displacement of whatever it's attached to. In this case, it's attached to link 4 and is measuring, I'm sorry, I misspoke. It's attached to link 2. It's measuring the displacement of link 2 and attached to ground at the top. And we also have, in the back, not visible from the present vantage point, an LVT, linear velocity transducer. So we're able to measure position, velocity, and acceleration, plus torque, if we wish, simultaneously on this machine. And these are all brought out down here on the front panel, where these various taps allow me to bring those over to an analyzer, which we'll show you later on. There's another shaft encoder not visible from your present vantage point, identical to the one I showed you earlier on this end, and having two shaft encoders allows me to measure the torsional deflection of the shaft dynamically. So I can look at the difference between the pulse trains coming out of each of those shaft encoders in a special piece of electronic hardware and look at the time phase shift of the two signals, and that tells me what the twist in the shaft is at any given instant. The reason there are two cams on this is to provide us a means to demonstrate the effectiveness of what's called a torque compensation cam. The cam on the left I'll refer to as the primary cam. That has a program on it which is 4 motions, 2 rises and 2 falls, interspersed with dwells. So it's rise, dwell, fall, dwell, rise, dwell, fall, dwell, repeating. The first rise is a 4, 5, 6, 7 polynomial. You can read about that in Chapter 9 of your Design and Machinery book if you're not familiar with that terminology. The second motion is a fall, and that's a 3, 4, 5 polynomial. The next rise motion is a modified trapezoid, and the final fall motion is a modified sine. And we'll see those on the traces of the analyzer in a few minutes. The primary cam that I've just described then creates a torque function which the motor must supply in order for it to turn. The compensating cam provides the inverse torque function. And that is, none of those functions that I just rattled off are on that cam. It is a special function that is mathematically calculated in order to give exactly the inverse torque to what the primary cam gives. That will effectively cancel the torque on the shaft, making the motor only have to provide whatever torque is necessary to overcome friction. I think we can run the machine now and show you something of what it does and allow you to hear it as well. It's currently set to run at 120 RPM, which is 2 cycles per second. And if you've already viewed the videotape of the 4-bar linkage, then you can appreciate that this is a good deal quieter than that 4-bar linkage machine, which had some serious backlash issues in the gear train. There is no gear train in this. It's belt drive from the speed control motor down below up to the flywheel, so we get around some of the backlash issues in that fashion. This machine is also made to a much greater degree of precision than the 4-bar linkage because it's intended to be a carefully constructed measurement device that we can take controlled measurements from to compare one cam design to another. It's made to accept commercial cams from a local company that has a lot of these cams on their production machinery, and we can take any of their cams in and test them for them in this controlled environment. It's much quieter here in a university setting than it is in a typical factory. So I think now that you've seen it run, which isn't very exciting, you see links going up and down over here. They're not really doing anything useful, but these transducers are, in fact, measuring what's going on dynamically in those links. So we're going to cut now and move over to the analyzer and show you what these traces look like as the machine runs. You're looking at the screen of a dynamic signal analyzer, which has been taking data from the machine as we were talking about it. It's a 4-channel device, and I've got 4 items here, but we're going to look at them 2 at a time. So what you're looking at on the screen right now on the upper trace is the displacement of the follower as measured by the LVDT that I described earlier. And you see it at a low dwell here, and then rising to the high dwell, remaining in the high dwell for a short time, falling on the first fall, again on a low dwell, another rise, remember it's a 4-dwell cam, another dwell, another fall. So there are 4 events, 2 rises, 2 falls. it's difficult to tell from the shape of the displacement curve what those mathematically are. That will be more apparent when we look at the higher derivatives, particularly the acceleration, which I'll show you in a second. The lower trace shows the velocity, which is, of course, the first derivative of the displacement, and therefore it is thus the slope, and therefore you should expect to see where you have positive slope here, a positive value here. In fact, I can use the cursors to show you that. If you can see those little diamond-shaped things moving along, that's the cursor, and I've got them coupled together. So I'm turning a knob off camera to move those. And as the velocity begins to go positive, you see the displacement simultaneously going positive. And when we get to the halfway point up the hill, right there, you should expect to have peak velocity. That's the inflection point, and you do. And then the velocity falls back to zero as it gets to the top of the hill, and the velocity is zero in the dwell. Now notice right here in the middle of the dwell where I'm putting the cursor now, I'm going to move the cursor away because it will hide the effect, and I'll use my pencil as a pointer. There's a little bit of a glitch right there, and there's another one over here in the middle of this other dwell. That's evidence of the crack in the cam. I told you before that the cam is a split to be assembled onto the shafts conveniently. And that split, as the roller rolls past, creates a disturbance, and we'll see that even more so in the next derivative. So here we have a positive pulse of velocity for the rise, a negative pulse for the fall, a positive pulse for the second rise, negative pulse for the fall. I'm going to move now to another screen, which will show you the acceleration traces. On the top trace, we have the raw acceleration coming from the accelerometer that you saw earlier. And you'll notice that it's quite a bit noisier than either the displacement or the velocity curves, and that's for a couple of reasons. One is the accelerometer is more sensitive to vibration than either of the other two devices. And also, as you go up in derivative, there is more information content. This is the second derivative of displacement. And you're seeing some vibration during the dwell, and then a pattern, a shape of positive, negative acceleration for the first rise event. It may be hard for you to recognize that from its shape, but I can tell you it's a 4, 5, 6, 7 polynomial curve. Then you have the next dwell, and in the middle of the dwell now you see very large evidence of that crack. The crack is causing the accelerometer to be excited as the roller passes over it, and it rings the system. And the follower train is vibrating in a classical exponentially decaying fashion. You see what essentially looks like a sine wave of oscillation there that is falling off, not quite to zero. It doesn't damp out fully before the next event comes along. And the main reason why this 3, 4, 5 polynomial fall is so noisy is because this impulse that occurred in the middle of the dwell has not fully wrung out, and it is exciting all the way through the next fall event. The next dwell does not have a crack in it, so it doesn't quite excite things as badly. Then we come to the modified trapezoid rise, which also has a lot of ringing on it. That's in part because of the roughness of the jerk in the modified trap function. And here we are at the second crack on the other side, 180 degrees away, and that again rings the system quite drastically. And finally, we have a modified sine fall. Now, this is typical of the kinds of traces you get from accelerometers in real machines. In fact, this is relatively quiet, that is less noisy in terms of these oscillations than you would see in a real machine, because we have here a laboratory instrument running in a quiet environment. Now, we can see better what we have for acceleration by using a filter. And I've applied a filter to this system, and we can move over and show you that filter box in a moment, but the result of the filtering is to remove the high frequency information. And this is the same function down here as here, but it's been run through what's called a low-pass filter. And that's taken out all the frequencies above. I set it to about 110 hertz. This is running at 2 hertz as the fundamental frequency, 120 revolutions per minute. So I've taken out everything from 55 times that up.
And that's cleaned it up remarkably, and it now looks a lot more like what you would see in your textbook for 4, 5, 6, 7 rise. That looks a lot more like a 3, 4, 5 polynomial. That happens to be a fall. The glitch due to the roller passing the crack is now much reduced because the high frequency has been taken out of it. The modified trap in its filtered form doesn't look quite like the textbook. Notice how much noise there is on the top of that, and the filter is essentially just putting a line through the middle of that noise. So rather than the flat top that it should have from the textbook standpoint, it has a bit of a slope that does not really belong there. This one doesn't look quite so bad because it isn't as noisy on that second pulse. Here's the crack in the cam again, and here's the modified sine function, which is the last one on the cam. Now let's move to the filter, and we'll show you how that operates.
It's an electronic device that allows me to bring a signal in, and this wire that you see on this port is bringing the acceleration into this box, and this wire over here is bringing it out after it's been filtered. And this is an adjustable filter. I can turn these knobs and change the frequency in hertz at which it begins to filter. And I can also make it be a low-pass or a high-pass filter. I have it now set to a low-pass configuration, and that term is self-explanatory. It says it lets the low stuff through and shuts off the high stuff. So this is going to filter out above a certain frequency, and the frequency that I have it set to is 110. These numbers are multiplied by 10. So I have 110. 110 hertz, which is relatively low. Now, I mentioned earlier that this machine is running at 120 RPM, which is 2 hertz. So this 110 hertz is 55 times the basic speed of the machine. So I'm able to filter out anything with higher frequency than about 55 orders by setting the filter to this position. And I played around with that earlier. If we come back to the other screen to see the result, I just tailored that cutoff frequency until I had a reasonably clean image of the acceleration. Now, where that cutoff would have to be would vary with the particular machine on a particular day, perhaps, depending on how much vibration was present. But now you see a much more typical shape of a 4, 5, 6, 7 polynomial here. Still some noise on the 3, 4, 5 polynomial. You can see some noise on the modified trap. And here is the modified sine. If you're not familiar with those terms, then you perhaps should read Chapter 8 in your textbook, which will explain them to you. Now, in the middle of the dwells, you see a glitch corresponding to the glitch here, which is much larger in magnitude in the unfiltered data. This is the raw data. This is the filtered data. If you run Program Dynacam and input the file that's provided with this lab for you, you can generate the theoretical acceleration for this cam, which will look very much like this filtered version. You will not have the little glitches in the dwells because the theoretical one does not know about the split in the cam. So one thing you can take away from this is the revelation, perhaps, to you that the theoretical curves that you calculate with such tools as Dynacam give you rather a optimistic view of what the real system is going to do. This is a very typical acceleration measurement in a cam follower system. It has noise on it. It always will. It's very difficult to get anything to run completely quiet. This, remember, is a very quiet machine compared to a real machine in an industrial environment, which would have much more vibration on it than you see here. That noise, as so-called, sitting on top, is coming from a number of sources, some of which have to do with the surface finish of the cam, which is not perfect, but some of it simply has to do with the vibrations inherent in the structures, which are the links that are riding up and down in response to the cam motion. Program Dynacam will actually simulate those for you if you use the Vibrations tab and give it information about the mass and the springiness of your follower train. It will simulate this curve with the noise on it. Okay, that should give you some sense of what happens in a cam system when you measure the actual data. To sum up, when you look at the displacement, which is here, and the velocity, you see quite clean signals, in part because those signals have lower information content physically, in part because the transducers that are typically used to measure them are less sensitive to high frequencies. When we move to the acceleration regime, we see a much more realistic picture of what's going on in a vibration sense in the machine, which we can filter out to make look pretty, but recognize that we are hiding information in this filtered signal. Well, this laboratory can be run virtually by using the data that's on your disk in the book. I've provided you with these traces, and you can take those into Excel and look at them and plot them. And you can also compare them to the theoreticals generated from Program Dynicam, and that file, as I mentioned, is also provided to you. So if your instructor wishes you to do so, you can run this lab in somewhat the same fashion that I have my students do here at WPI. Have fun doing it. We'll see you again another day.